Welcome back to lesson 5, and in this lesson we'll try to continue from where we left in previous lesson by looking into actions 5, 6, 7 and 8. But before that we'll look into a little bit of background. Consider an object or a system of objects, later we call it a free body, onto which there are several forces acting on. Okay, these are the several forces which are acting on the body. Let us call them F1, F2, F3, F4 and so on up to Fn. Okay, we want to see if we can simplify the situation by finding one single force which will replace the effect of all these forces. Okay, if we can find one such force which will replace the action of all such forces, we call it resultant of the system of forces. Of course, you may have a couple also along with it. In general case, we'll come to all that specifics later, but for now this resultant will replace the action of all that forces. So whether you say n forces are acting or whether only the resultant is acting, it's really the same. So the situation is greatly simplified. To allow us to do that, you have all these axioms. Okay, these axioms define rules using which you can find the resultant of a system of forces, and also it will allow us to compute under what conditions the resultant could be 0 or the magnitude of the resultant is a specified quantity and so on and so forth. So let us try to look into these axioms, beginning with axiom 5, which is transmissibility. Okay, when you say a force, you need to specify several things. You need to specify its magnitude, you need to specify its line of action, which I call it action line. You need to specify its point of application, and you need to specify its direction, left or right and so on. Okay, this transmissibility principle says that you can move the point of application anywhere along the line of application and keeping the effect the same. Okay, to see that, let us say you have a body, okay, on which you have a force F. Okay, now it is our common sense that either you can apply the force at this point of application, or you can tie a string at this point, then a long string at the end of which you try to pull onto it. Both are the same, whether you hold here and pull, or you tie a long string and at the end of the string pull. Okay, the principle of transmissibility is kind of an extension of this common sense principle, which you says if you have the line of action of the force along this, you can move it anywhere. For example, you can move it here, okay, and say that the effect of force here or here, it's the same. So safely you can erase this force and say that this is the force here, or if you want, you can tie a string, a long string, okay, long string, and at the end of this you tie a long string, and at the end of that you try to pull onto it. So whether you apply the force F here or whether you apply the force F here, it's really the same. Okay, The second axiom, in fact the sixth axiom, number 6, it will try to give us how to add vectors vectorially. Okay, let us look at this. Let us say you have a object which is acted upon by two forces. Okay, let us name them as F1 and F2. Okay, so to add them and find the resultant, again recall, when we say resultant, what we mean is that single force which will replace the effect of both these forces. Okay, you extend this back, move the force back to this point O, move the force back to this point O. Note that you can move them along here because we already have principle of transmissibility which says that as long as you don't change the direction of the vector, magnitude of the vector, you can move the forces back or forth along the line of action. So you have one vector going from, let us say, O to A, another vector going from O to B. To find the resultant, you will draw a line here parallel to F2. You will draw a line here parallel to F1, having them meet at, let us say, some point C. Now you draw from O to C. This will give you the resultant R. Okay, and vectorially, if we say you have R bar is equal to F1 bar plus F2 bar. Okay, strictly speaking, we need to put a arrow here, we need to put a arrow here, we need to put a arrow here. But where we understand that this is one vector, this is another vector, this is the resultant vector, we often omit it because we understand it from the context. Note that the magnitude of R bar, which is the length of this line segment from O to C, is not equal to magnitude of F1 bar, which is the length from O to A, and F2 bar, magnitude of F2 bar, which is the length from O to B. So this process needs to be understood as vectorial addition. This addition is not a simple addition process. We'll try to see in subsequent lessons how to use this to find the resultant of a set of forces. Okay. The next axiom says something about equilibrium. Okay. Let us say you have one object, okay, with a force, let us say P bar, acting on it. Okay, if only one force P bar is acting on it, obviously this object will move along the direction, provided it has a constant mass, it will move with constant acceleration along this line. But if you want to keep it in equilibrium, we know pretty well that you need to apply one force Q bar here to cancel the effects of P bar. To cancel the effects of P bar, what must be Q bar? That is what is specified in this axiom. Okay, to cancel that, this Q bar must be equal in magnitude, that is this magnitude of P bar should be equal to magnitude of Q bar. Then P bar and Q bar should be collinear, and they must be acting in opposite directions. If these three conditions are satisfied, the effect of this P bar is completely nullified by the effect of Q bar, or vice versa. If Q bar is the force we want to cancel, P bar is the force. This in some sense says that when both this P bar and Q bar are acting on it, on this object, the net force acting on the object is 0. Both of these cancel out. So in some sense, this law strikes an analogy between equilibrium of forces and zero as a number. Okay, but for now we need to understand that if you have a force P and you want to cancel the effect of force P by a force Q, the conditions to be satisfied are the magnitude should be the same, they should be collinear, and they should be acting in opposite direction. We'll try to see how we apply this in subsequent lessons, and we'll look at the next axiom, that is axiom 8, which is law of superposition, okay, which says that when you have a system which is acted upon by whatever n number of forces, okay, F1, F2, F3, so on, n number of forces it's acted upon. This is one object, and you have a system of forces, let us say 2 forces, okay, P bar and P bar. Strictly speaking, we need to call it minus P bar. Okay, you have a force P bar here, and you have a force minus P bar here. Okay, obviously you know the net force that is acting over here is P bar plus minus P bar, which is equal to 0. And we know that if we add 0 to anything, you will get the same quantity. If you subtract 0 from anything, you will get the same quantity. So what we mean is this X is one object which is acted upon by all these forces. This 0 is the system of forces in equilibrium. If you take this whole and take this P bar and minus P bar, put onto this object, it really doesn't change anything, because we know x bar plus x plus 0 is x, x minus 0 is x. Because we are adding a 0, in some sense we say that this system of forces in equilibrium is 0. It doesn't change the situation in any way. In fact, you can slightly modify this system of forces to be something like this: a Q bar and minus Q bar. Okay, you can now take this whole system and apply here, because you're still adding a 0. So you can say Q bar and minus Q bar. Okay, this whole system is in equilibrium, so in some sense it is 0. The system of forces is x, so x plus 0 is x, so the situation did not change. Or you can subtract. For example, you can take out this Q bar and minus Q bar and say that the net effect is the same. Whether you have these or whether you don't have these, it really doesn't matter, because you add a 0 or subtract a 0, it really doesn't change anything. Okay. With that, we come to the end of lesson 5. In subsequent lessons, we'll try to see how to apply these axioms to practical problems in engineering mechanics, in simplifying and perhaps in finding solutions and designing. Thank you very much for staying. Have a good day.